Morning, guys. So yesterday we took a quick detour into the physics. We started looking at electromagnetic waves, or all the different forms of light. It turns out our visible portion is actually a really tiny portion that we can see. There are some that have less energy, like infrared rays, like microwaves and radio waves. Things that are more energetic than even the purple end here. We have the beyond violet, so ultraviolet end. We have the X-rays, we have the gamma rays. We found that all of that light traveled at the speed of light, c, when we have these constants here in our data booklet. We had to look at a little bit of the terminology behind waves. We labeled things like crest and trough and amplitude. We came up with a few equations to actually link terms like frequency with energy, ideas like that, because ultimately when we actually look back at the Bohr model, when Bohr did his experimentation, he started off with an element. He used electricity here to actually excite these electrons. Temporarily, we can get those electrons to actually jump up into higher energy states. Those states there are excited. They're going to be more energetic. And depending on how those electrons ended up falling back downwards, they ended up giving rise to what's called a line spectrum. So let's just do a quick recap there, and then we'll switch over to today's lesson here. So imagine every single element has an energy level diagram. Basically, the lower energy, the more stable it is. I always picture the nucleus to be somewhere down here. What we're plotting, instead of drawing the circles around the different nuclei, I'm plotting, if I'm on shell number 1, I'm this far away from the nucleus. What's my potential energy away from the nucleus? I should be the most stable, so I'm going to be less energetic. In fact, every element has an infinite number of shells available. So that's shell number 1, shell number 2. We notice that as we start getting farther and farther away from the atom's core, the shells actually get closer together. That's to make sure that, yes, I can have an infinite number of shells, but because there's only so many protons in the core, the atom's size can only get to be so big. So we have this sort of staircase diagram. Remember, Bohr didn't know anything of this. He looked at the data, he looked at his experimentation, and this is sort of what he concluded. For some reason in our quantum mechanics, every element has a staircase sort of related to it, that if, let's say I had hydrogen, I have an electron on shell number 1, if I send in exactly the right amount of energy, and it's exactly the energy to traverse one of these gaps here, the electron can actually absorb that energy. There's our first main word here. We wrote down absorption means you jump to a higher energy shell. It can actually jump from, let's say, shell 1 to shell 3, or even beyond from there. But that takes a very specific amount of energy. That means the electron would now be on shell 3. Well, there are spots that are actually close to the nucleus. The electron here, like I mentioned, is currently now in an excited state. It's further from the core than it needs to be. It's higher energy. Eventually, it gets bored, it gets tired. We can just draw the staircase backwards here. The electrons will then want to relax. It wants to go back to its shell number 1. It's going to be close to the core, attracted to the core here. Depending on how it actually jumps backwards, gave rise to a line spectrum. So for example, when it jumped from shell 3 to shell 1, that is a very big energy gap, but it's also a very unique energy reading. So in the visible portion here, when we pulled out our spectroscope here, we saw that electrons are stuck on the atom. It's not like electrons can leave, but electrons, as they actually fall to a lower shell, they end up emitting, releasing light of a very unique color. This light photon here will have exactly the color as dictated by the size of this delta E here. So depending on how the electron ends up falling downwards to a lower shell here, let's say instead it did the temporary, let's go 3 to 2 first. Well, I also need to get back energy. When that photon ends up leaving, you notice that this energy spacing is not as big. The photon of color is also not as big. Make sure when you're labeling these line spectra here, you label the different sides. So far here I have the low energy, like the red side. The high energy here would be the purple side. Right? And we had the, 2 to 1, I'm not quite done yet. I can still be closer to the nucleus. I can jump this gap. This is sort of somewhere in between that red and purple. We saw that the photon color that actually leaves maybe for the 2 to 1 gap here is actually a greenish color. Because the energy shells are actually converging or getting closer on the higher side, we see that with the converging of the line spectra as well. But the big sort of breakthrough for Bohr was electrons are sort of strange. Every element has a staircase versus a sort of ramp idea. If elements actually had a ramp, let's see what would happen. If I were on shell number 3, being on a ramp, I could hypothetically get to, let's say, shell 1.5. I can actually stop there. And if I can fall down that shell, I can actually give you not just that purple color for 3 to 1, I can give you some of these in-between colors. What Bohr did is he said, oh, because elements give me line spectra, he said, no, we're actually not like a ramp diagram. There actually is no in-between step. I can't jump 3 to 1.5 just because I want to give you that in-between color here. There's nowhere to land. You can jump 3 to 1 all you want, 3 to 2 all you want here, but you can't actually jump in between, which gave rise to your line spectra, which gave rise to the individual colors, and the colors exactly matched the bands, the sizes of these energy gaps here. In fact, we'll do this a little bit more in chapter 3. We can also think about if it was a staircase going down, it was a staircase going up as well, which means the energy has to be perfectly the right amount of energy. Let's say purple, there's many different purple colors I could have sent in. If I send in energy that's a little bit too energetic, it would have taken you from shell 1 to if I could stand at shell 3.1. The electron couldn't take that because, again, the electron can't actually stand in that position. It actually has to be a really, really fine-tuned energy that I'm putting in, one unique wavelength of purple. That's exactly what it needs to actually jump the gap. What I want to introduce to you here is nobody has the time to do that, right? Nobody has the time to figure out, oh, what's the exact wavelength that you need? We'll see that a little bit in this lesson as well. What we're going to do instead for an absorption spectrum is we're going to cheat, let's just send in all the colors. Let's have the 700 nanometer side, the red side on one side. Let's have the 400. And instead of actually worrying exactly which energy readings I would need to send in, let's send in purposely white light. Let's send in the whole Roy, red, orange, yellow, green, blue. It's just always in this ordering here. Remember the sizes of these spacings here are not always the same. Let me just actually move this over here. So let's say that's the 400 purple end here. So let's purposely send in all the colors. And what this element is going to do is it's going to say, sweet, because I needed one exact purple color, no, it wasn't that purple, it wasn't that purple, oh, it's this exact purple color, it's going to actually absorb away that color will now be missing. Same thing with the red. Maybe there was a whole band of red, it could have absorbed any of those colors there. There's going to be one unique red that it's absorbing for, and it's going to absorb, it's going to eat away that color there. We also see one green color here, so it's going to eat away one of those green colors. Instead of sitting around trying to send in exactly the energy that it wants, I'm doing the catch-all. I'm sending in all the colors, and then I'm just going to expect it's going to be missing some colors. Those of you that are astute, you're going to be able to see, well, those colors are the very same red, green, and purple that I'm going to get back as the electrons actually fall downwards. So again, the general idea is electrons are stuck on the atom. They can absorb special colors or they can give off special colors. It's the photons that we're sensing. Our device there was called the spectroscope. For today, we're just going to put some numbers to this one here. Turns out trying to make predictions with how big these energy gaps are for elements here is actually really hard to do. But if I can make a few assumptions here, I can sort of get at an equation to get this relationship. So we're going to get into our lesson today here. We're going to call this section here the Rydberg equation or the Rydberg formula. You have to be careful when you, let's say even if you Google the Rydberg equation, sometimes the Rydberg equation is actually formatted in different ways. It's sort of isolated in different ways. And especially when we get to a Rydberg constant, sometimes their number is going to be different from the one that we see. Just based on our lesson here, I'm going to introduce to you, if I write the Rydberg equation in this way, the constant should be this number. So we're only going to be dealing with the Rydberg equation in this fashion. Just be careful. Other textbooks might do it a little differently. So for the Rydberg equation actually gives us a relationship between the wavelength of the photon released or absorbed, right? It's the same energy gap. Relationship between the wavelength of the photon released and we can just say the energy spacings and the energy gaps. Just to forewarn you, this formula looks a little bit scary, but as you get a little bit more practice with this, it's not all that bad. So I mentioned here, this formula here in general will be really hard to talk about. We need to make a few simplifications. The simplification we're going to make here is this equation that I'm going to give you. We're going to assume we're only looking at, assume we have a hydrogen-like species. So what is it about hydrogen that we like? Hydrogen only has one electron. Now, what's so good about having one electron? Remember, hydrogen, even though in ground state, I would expect that electron here to be on the first shell. That electron, what we're doing in this lesson here is we're exciting this electron, we're letting it relax and fall down lower shells here. this hydrogen already has the infinite shells. I'm interested in, as it jumps up and down the staircase here, what colors of light does it absorb, what colors of light does it give back. But this is nice because I just have a single electron. There's just one person that's jumping up and down the staircase. Even if you go to helium here would actually have 2 electrons. The dynamics of this gets to be a lot more complicated because, yes, helium itself would have its own energy spacings. That's why we can sort of use its line spectra as a different fingerprint for helium. But depending on this electron here, I can still jump up and down. I can absorb energy, I can release energy, but I'm always going to be keeping my peripheral vision. I want to see where the other electron is. So say for helium, the electron was on shell number 3, I might notice, hey, the other electron is on shell number 1 already, although ultimately I'm going to pair up with him. Maybe I want to do 3 to 2, a little bit more common. So you see that even having that one extra electron, it changes all the dynamics. It makes it so much more confusing. Why don't I just say then, just hydrogen? This formula only works for hydrogen. Well, there are other ways. Could I make helium have only 1 electron? Well, what would I do is I would take helium. Let's remove an electron. Let's make it helium plus. Again, that's a really weird thing to say because helium, normally when it bonds, it doesn't bond. It's 0 charge. But again, I'm artificially coming in. I'm ionizing its electron. I'm pulling off this electron, so I'm getting charged. So this formula we're going to work with, sure, it works for hydrogen. It works with something like helium plus, lithium plus 2, and so on and so forth. Not the normal charges that these things would have, but basically it's when these things here would only have a single electron. This formula only works when there's only 1 electron that's dancing around the different shells without regard for extra repulsion from other electrons. Now, to be sure, in our lab, we could do samples of what does helium spectrum look like? What does lithium's actual sample look like? We can do spectra for the different elements. It's just that the formula I'm going to give you doesn't accurately give you those numbers. So yes, they also give you line spectra. Yes, they also are a fingerprint, but just this next formula that we're going to see doesn't work for those. For, under that assumption, a hydrogen-like species, here's the Rydberg formula. I'm going to write it for you this way. 1 over lambda. You're already scared. Okay, why don't I just say lambda equals? Turns out, you'll see in a second here, 1 over lambda is proportional through a Rydberg constant R. Careful, this R is not the ideal gas constant in chapter 1. I'm going to give you this in a second here. It's going to be R Z squared. Z we had used for atomic number. And then we're going to match it up here with a 1 over Ni squared minus 1 over Nf squared. So that is the way we're going to formulate the Rydberg equation. Let's see if we can dig through the terms here. Lambda here is wavelength, right? Wavelength is should be in meters, right? It's a distance crest to crest. R, I want to be careful here. This is going to be Rydberg's constant. So this one here is not the ideal gas constant. The Rydberg constant here in this formulation, 1.097 times 10 to the 7 meter minus 1. That's the unit. Z is the atomic number, like we said. This is the actual number of protons. I know I want to be hydrogen-like, but I could still have 2 protons for helium or 3 protons for lithium. That Z needs to go in. You square that number, no problem. What have we been using N for so far? Right. In chapter 1, we had used it for mole. In this chapter, we've been using N for the shell number. So you can actually guess here, Ni actually stands for my initial shell, my starting level. Where am I beginning from? And NF is actually my final level, my final orbit, my final energy. And it's just this comparison between Ni and Nf. Why do we leave it as this 1 over lambda? Let's actually do a quick question just so that we can understand this, and then I'll come back to that question. So for a hydrogen-like species, I want you to calculate here what photon wavelength, so what color, what photon wavelength is released when an electron falls from n equals 5 to n equals 2 on hydrogen. So I'm just totally making up some numbers here. We can draw a picture to that. This should be fairly easy. We can do our energy level diagram. We have energy shell 1 down here, 2, 3, 4, 5. So this time, my electron happens to already start on shell number 5. It's only going to drop to shell number 2, right? It's not going to fall all the way. We know we're on hydrogen, so I know my Z value is 1. And I want to know, well, what's the wavelength? So let's do it here. 1 over the wavelength is RZ squared, 1 over Ni squared minus 1 over Nf squared. Let's just plug our way through here. 1 over lambda is 1.097 times 10 to the 7. Z is 1 for hydrogen squared. 1 over, I'm starting from 5 squared and I'm ending at 2 squared. So let's just work through the algebra. 1 over lambda is equal to, I would usually just type in this part first. Don't be scared to type it in like 1 over 25 minus 1 over 4, right? That way I can just get a decimal. That part there gives you negative 0.21. I'm going to scale it by Rydberg's constant times 1.097 E7. I'm not quite done though. This is 2303700. This is still 1 over the wavelength. I still need to take the reciprocal of it. 1 over this 2 million number here gives me the wavelength. It's negative 4.34 times 10 to the negative 7. Right? In this case here, well, lambda is a distance. We're expecting it to be meters. But because it's a distance, I would expect it to be a positive number. Why am I actually getting a negative number out of this? Or what does the negative actually tell me in this formula? Now, we are used to, especially when we're talking about light, talking in order of nanometers. So 434 nanometers is what it's looking like. So sort of this is the purple color light, purple color side. What this negative actually represents is, especially as the electron falls, because this photon here actually leaves, it actually takes energy away. So in this case here, I'm not suggesting somehow the crest-to-crest distance suddenly has become into the negative. The wavelength is actually a positive 434. Remember, that represents the amount of energy this photon carries. As the photon actually leaves, it's actually going to carry this energy away. So let's just write down in words here. The photon removes, or takes away, removes 434 nanometers worth of energy. Now I know that's not exactly an energy term. We'll do that in the next question. Worth of energy from the electron. Right? So when that photon leaves, it's a wave, it carries energy. This time it's actually carrying energy away. It's going to remove 434. This negative actually just implies here energy is actually released. And energy will always be released whenever we deal with an emission, whenever we deal with falling from a high shell to some lower shell. So that just sort of gives you some introduction here. No, it's not that distance is negative. That negative just means emission. Now, why do I leave this here in 1 over lambda? A little bit of algebra, and then we'll do another question. We can start off with our Planck equation. So we saw this from yesterday. Let's go. The energy of a photon is proportional through the frequency. It's h times f. We also had the universal wave equation, which says c is equal to lambda times f. What I'm going to do is I'm going to rearrange this universal wave equation. Let's say f is equal to c over lambda, right? So wherever I see f, I can actually punch in c over lambda. Well, I see a c over lambda, I see an f right here. Let's just plug that in. So we'll have here h, then we're going to have c over lambda in brackets. I'm just going to slightly manipulate that there. So I'm going to pull the c term out. So I'm going to h times c, and then we're left with 1 over lambda. And then now we say, well, where do I see a 1 over lambda? Well, Rydberg tells me 1 over lambda is actually this horrendous mess. I can actually punch in this term into that 1 over lambda part. And this gives us our final equation here. We have hc, the rest of it ended up being rz squared, 1 over ni squared minus 1 over nf squared. Usually this is sort of the full Rydberg equation here. Usually they even say it to you as delta E, because this energy gap here is either positive or negative, just depending on absorption or emission. So positive would mean absorption. So I go from a low N to a higher N, a low shell to a higher shell, or it's either going to be negative for an emission, and I'm going to fall from some higher N, high shell to a low shell there. So the delta E is equal to hc rz squared, 1 over ni squared minus 1 over nf squared. Basically what this is saying here is this is going to give us a relationship between, I know my energy level diagram, every element has an infinite number of shells available. If you pick out any gap, let's say I pick out 2 to 4 here, if you can pick out ni and you can pick out nf, whether I jump up or jump down there, it's a relationship between what the electron is doing jumping up and down, and it's linking it to how many joules of energy does this photon that gets released, or the energy putting in, how much specific energy do I need to put in so that it's exactly the right amount the electron can actually jump up the gap there. So let's just practice through a quick question here. How do we sort of utilize this formula? I want to make one other observation here. You're going to find that in this formula, basically all these numbers are positive. If you look here, Planck's constant, 6.63 times 10 to the negative 34. C is the speed of light, 3.0 times 10 to the 8. R is now Rydberg's constant, 1.097 times 10 to the 7. Atomic number here, that's going to be a positive, right? That's the number of protons. The ends are also positive, right? Shell number 2, shell number 4, those are positive. So let's take a look here. How is it possible I can have a delta E either positive or negative? The sign part actually really comes down to this latter part here. Every time, like in this question here, if I go from a higher shell to a lower shell, when I take a square, this denominator is going to be bigger than the other one. When I take 1 over a big number, that fraction actually becomes tinier than the other fraction. That's actually where I pick up the negative. So this is the part that actually tells me, depending on the ends, I already wrote the conclusion for you here, depending on whether I'm falling, I'm going to pick up a negative there, or if I'm absorbing, if I go from a low shell to a high shell, 1 over a small number minus 1 over a big number here, it's going to end up staying positive. So that actually usually comes out of the math here. I'll do one question like that, one question where we'll actually put negatives to it, just to give you some familiarity with this formula. So based on that there, let's just make up a question here. I want you to calculate the energy required to promote. That's just the language that we use. We're going to give it the energy that it wants so that the electron can actually jump up. Promote an electron on helium plus, just to show you that it's a single electron species. Yes, the atomic number is different. I want to promote an electron on helium plus from, let's go from n equals 3, let's go bigger, n equals 7, right? So again, the picture is not all that hard. We have an energy level diagram. I have all my sort of energy spacings here. You don't always need to draw kind of shell 1, 2, 3, whatever, but so far what we're doing is we're starting from electron shell number 3, shell 4, shell 5, shell 6, shell 7. I want to give it exactly the right amount of energy, right, of exactly the right joules, so that it can jump up the staircase and exactly land on shell number 7. No more, no less. It won't absorb it. It won't take it if I don't. So let's just try out a formula here. We're going to have just our delta E, the size of the gap, is equal to HCRZ squared, 1 over Ni squared minus 1 over Nf squared. I'm going straight to this fully derived formula because they want to know energy in relation to the transition. If you look back at the earlier question, it was just wavelength with which particular transition. You're more than welcome just to use just the Rydberg equation by itself. So let's just punch our way through the constants here. 6.63 times 10 to the negative 34. That's the Planck's constant. Speed of light is 3 times 10 to the 8. We were just saying these numbers here are all, they all happen to be positive. The Z for helium is 2, right? Atomic number 2. We need to square that. And then we have a 1 over, I'm starting from shell 3, square it, and I'm ending at shell 7, so 7 squared. Sometimes people like just typing this number in. It's like, yeah, I know it's made out of a bunch of constants here, but every time I do Rydberg, I'm always scaling up by Planck and speed of light Rydberg. Sometimes people like typing this part, all the power to you, 6.63 e negative 34 times 3e8 times 1.097 e7. So that part there, if you want just one big constant, 2.2 times 10 to the negative 18, but you do need to be careful. What can change from problem to problem is we might be a different element, so we might have a different Z, and what will definitely change here is which gaps I'm actually jumping from. So I'll probably just type in this part as well. I'm going to go 1 over 9 for 1 over 3 squared, minus 1 over 49 for 1 over 7 squared. Notice this part here ended up positive. As you would expect, when you go from a low shell to high shell, I need to actually input in the energy. When you type this all in one, try to type this all in one row here so that we don't have any problems with rounding. Times it by 1 over 3 squared. Double check my numbers. I'm getting here, the corresponding energy here should be 7.9 times 10 to the negative 19 joules. Right? So that's going to be 2 sig figs here. In case later on, I know I was just asking for energy in this case, so this was positive. We know it to be absorption. In case later on they asked you, well, could you then find the wavelength, or could you then find the frequency? Once you have this energy here, it's sort of like undoing this formula. Yeah, you can do the E as HF, factor Planck's constant out and get F, and once you have F, you can go C is equal to F lambda. So it really just depends on the question. You can sort of take those out of the formula again and get it. Re-express in terms of frequency, re-express in terms of wavelength. Pretty much if you have one of the numbers, you can get the other ways of expressing them. Let me just do 2 more questions with you. This next question here, I want you to calculate the 4th line in the Lyman series. Right. Huh? Don't I need more information there? Okay. They do say in the new curriculum you don't really need to know those main terms, Lyman, Balmer, and Paschen. They'll hint at what it is. But since we did it, let's see if we can dissect this number. I'm interested in calculating, so maybe the energy, maybe the size of the wavelength, whatnot. I'm interested in calculating it for the 4th line, for the 4th transition in the Lyman series. What does this word here, Lyman, tell you? For our series, Lyman told you this was going from some higher shell n, jumping down to shell number 1. Right? These are the biggest gaps. Lyman also refers to specifically for hydrogen. If I'm a different element, I actually would have it's named a different series. So what I mean by 4th line here is if I draw an energy level diagram, I have shell 1, 2, 3, 4, 5. I don't mean lines in the sense of where is this energy or where is this energy. Remember, I don't really care about the exact energy. What I care is, especially when electrons are jumping up and down the gap, what's the first line? The first line, the first option in Lyman series is jumping 2 to 1. Well, not that one. Second line is 3 to 1. Third line is 4 to 1. Oh, my 4th line is actually trying to tell me I want to jump from n equals 5 down to n equals 1. I'm guaranteed the last one is n equals 1 because this has to be Lyman series. So I could have worded that here. Can you calculate the energy, the wavelength, the frequency for jumping from n equals 5 to n equals 1? We can start off just with our plain old Rydberg equation. We don't always need to go straight to this formula. Actually, I want to show you something with that, so let's do this. I want to calculate here. So delta E is equal to HCRZ squared 1 over Ni squared minus 1 over Nf squared. All right. So I'm going to try it out. We basically know all these other constants. So 6.63 times 10 to the negative 34. Speed of light is 3 times 10 to the 8. Rydberg constant 1.097 times 10 to the 7. These are all in SI units here. Z is atomic number 1. And then we're going to punch in just our 1 over Ni squared minus 1 over Nf squared here. I want to start from shell number 5 and I want to go down to shell number 1. Right? So just crunch our way through here. I would just type in this last part, 1 over 25 minus 1. This last part just becomes 0.96. No real surprise, it came out negative because it should be an emission process. So that just means emission. Let's rescale it by all these constants here. So times 6.63e negative 34 times 3e8 times Rydberg. And I'm getting the corresponding energy to be negative 2.1 times 10 to the negative 18. Do double check my numbers here. That gives me joules. And basically, as the electron falls, remember the electron is stuck on the atom. As the electron falls, it ends up radiating, releasing off an energy. That's energy that's lost to it. So this energy is released during the emission to the surroundings. Again, per photon doesn't look like a lot, but every time this electron jumps the gap, it's always going to give this unique energy reading. This energy can stack up really, really quickly. Let me end off with just one last question. Right before we do that here, I meant to say, well, if you know the energy, then we can find the wavelength, then we can find the frequency. All of that was sort of neatly tucked away for us in that formula. What I just mentioned earlier here is if I know the energy, I can factor out Planck's constant. I can say, well, if the energy is 2.1 times 10 to the negative 18, you'll notice I dropped the negative here. I already know negative just means this photon here is leaving. So photon leaving, it's taking energy away from it. Then it's just taking away that positive amount of energy away from my system. I can basically rescale out Planck's constant, 6.63 times 10 to the negative 34. We had multiplied it in to actually get to the energy. If you want to find the frequency, however, you just want to divide that term out. Divide by 6.63 e negative 34. This gives me here 3.2 times 10 to the 15. Remember, frequency is a measure of how many times do you bob up and down with this metaphorical wave here. And then if you have frequency, our universal wave equation will actually give us the link to get to wavelength. So if I want to just isolate for that here, C is equal to 3 times 10 to the 8. Again, C was another one of those constants I put in. If I want to regain the wavelength term, it's basically I'm going to pull that C term back out. I'm interested this time to find the lambda because they didn't really specify what I'm trying to do. Is energy, is a frequency, is a wavelength. Let's just find all of them for you here. 3.2 times 10 to the 15. Keep the whole number in your calculator if you can, so we don't accumulate any rounding errors. 3e8 divided by that, and we're getting here 9.5 times 10 to the negative 8. That would be in wavelengths, so that would be in meters. And if I were in nanometers, this is now 95 nanometers. If you look at the electromagnetic spectrum, 400 was already the purple end, was already the really energetic end here. This is way into the, probably still the UV region. I'm going to end off today's lesson with one more question. Your worksheet here will have much more practice. This last question here is sort of worded a little strangely. And what I'm going to ask you here is, what energy is needed? What energy is needed to ionize hydrogen? We will come back and talk about a guy called ionization energy towards the end of this chapter and more so in chapter 3. But basically for now, I want to make an ion of hydrogen. And what I'm going to do here is I'm actually going to try to think about completely removing that electron. So the Bohr model picture is quite simple. So I have hydrogen and electron on the first shell here. I want to figure out if I came in with a pair of tweezers, I grab this first electron, I want to pull this electron off. How far do I need to pull it so that I can completely ionize the electron so that the electron doesn't belong to hydrogen anymore? Note that on an energy level diagram, right, it sort of plots, well, we have energy shell 1, 2, 3, to infinity, right? So hydrogen's electron is currently on shell number 1. What shell NF do I want to be so that the electron is completely off this diagram? It's not even on hydrogen anymore. So I know my Ni is no problem. Ni would be 1 because that's going to be ground state. It's 1 or 2 close to the core. I don't want it on shell 2, shell 3, shell 4, shell 5, shell 1,000 maybe, shell 1,000,000, shell 1,000,000,000. Well, I know the shells themselves get stacked closer together. I actually want NF to actually approach infinity. Now, usually math with infinity is a little bit crazy. Hopefully, you'll be able to do that in some of your math classes. Fortunately for us, if you look back at the Rydberg equation, they actually make it a little bit simpler for you. Where the infinity pops up, it actually makes it easier. If I take this full equation here, delta E is HCRZ squared, 1 over Ni squared minus 1 over NF squared. If I just look at this, if the NF is supposed to approach infinity, my NF is right here. NF is going to get bigger and bigger. If I take infinity squared, it's still going to be infinity. If I take 1 over a number that's gradually getting bigger and bigger, let's start thinking here. Well, what if I had 1 over 10 to 1 over 100 to 1 over 1,000? As the bottom itself gets bigger and bigger, what is this whole term going to actually drop out to? Right? Hopefully you're able to say to me, that part there actually is going to approach 0. That actually makes my formula a little bit easier. So this delta E that I'm actually calculating, I'm going to give it a name. We're going to call this one here ionization energy. It's the energy needed to completely remove the electron, pull it from shell number 1 to infinity. It's actually just this first part, HCRZ squared, 1 over Ni squared. So it actually looked like it was going to be a harder problem here, but in fact it's actually not that bad. I'll leave it for you to type in. We know Planck's constant 6.63 10 to the negative 34, 3 times 10 to the 8, Rydberg constant 1.097. We are hydrogen, and we are actually on shell number 1. You can calculate the joules that's needed for this ionization. We're going to come back to this ionization. We're going to compare why ionizations are different between elements in a later lesson, but at least this is what we're addressing here. So practice your way through the worksheet and let me know if you have any questions. Thanks, guys. Take care.